Hello, my name is Per Nyberg. I'm a vice president with Quantum Machines, and today I'd like to speak with you about the road towards real-world applications of quantum computing. We're at a very interesting point right now in the market. Obviously there's a lot of discussion, a lot of, quite frankly, hype even around quantum computing. But there really is a lot more substance that's growing around things like the use cases and the potential has been now well established in a number of areas. There's been a lot of very interesting papers of late that have been published, and I think there's growing confidence and understanding of really what the opportunity is. So there's obviously a lot of fundamental research that's still left to be done, but there's less questions about if this is going to happen, but more about how, which is quite an interesting milestone that the industry has reached. And so with that, we're also reaching some very important inflection points. So one of them is really around, the first one is around, moving out of the laboratory, if you will, into commercial grade. This is obviously a very necessary step in any industry as, the technology matures and there's more and more demands on that technology to scale, be robust and to be installed in, customer, let's say, on-prem locations. The second one is really around the economics of scale. You hear a lot about things like qubit counts, for example, and obviously today we're at the tens or low order 100 qubits, and as we know, this needs to scale up into the thousands or many thousands or hundreds of thousands. And with that, people are really starting to understand, what quite frankly, the bill of materials is for building such a system. So it's more than just the fundamental research of how the quantum computer would work, but really about how you commercialize the technology to make it viable. And the third one is around practical quantum computing. You hear a lot of different terminology, quantum advantage, quantum supremacy, but obviously that's a little bit further out in time, and people are now talking more about practical quantum computing, and really, what are those first use cases going to be that do start to show some advantage, and really about what sorts of environments those use cases need to run in. There's also some trend lines that are developing that are kind of interesting as well, and this is really more as users themselves start to become involved in the industry. To date, there's been a lot of researchers and developers that have kind of dominated the discussion to some degree, and rightly so. But what's interesting is users become more and more involved in exploring the technology and pushing the limits of the technology. They also start to bring in their own requirements. This is, again, a very common sort of trajectory with any technology. So the first one is around, effective control. This is all around, the development and performance of applications, and really understanding the potential of the technology itself, and getting down to the absolute lowest levels of the technology. The second one is around integration. Clearly, a lot of discussion is around quantum being an accelerator. That is the likely scenario for quantum, is that it will be embedded or at least integrated into broader infrastructure. And this is something that is growing more and more over time. We see this today, especially in the high performance computing industry, where we talk about the integration of quantum and HPC. And the third one is heterogeneity. Again, there's lessons here from high performance computing. where, even today, you look at, a very typical high performance computing application, and it's composed of, x86 processors and GPUs. It could be specialized AI processors, different types of storage and memory hierarchies. And so this heterogeneity concept is very, very common today. And really what's going to extend with quantum is that it becomes one more piece of this heterogeneous landscape. But what's important here is that, thinking about how quantum will fit into this heterogeneous landscape. How is it integrated, as we talked about a second ago? And obviously, quantum is very much heterogeneous to begin with. Right away, talk about hybrid quantum classical algorithms and architectures that exist today. But in this context, it's really about heterogeneity at a whole different scale. So when you think about sort of the cadence of new technology adoption and integration, again, there's some very interesting lessons that can be gained from the high performance computing industry over a number of years. So typically, a good example is in the weather and climate prediction arena, where this is a very traditional use case in high performance computing. And I'll use a couple of examples from other technologies as they, explored new technologies, new novel technologies, and integrated them into their applications. So machine learning is an example. So traditionally, weather models and climate models were very much simulation based. And then over the last few years, with the advent of machine and deep learning, they started to explore the use of these technologies to do things like feature detection in hurricanes, for example. But typically, these would be explored standalone. And then over time, they would be embedded into the applications, and sort of a new term was coined called cognitive simulation. So now you have both, traditional simulation methods, very numerical based, combined with machine and deep learning embedded into the same application. And quantum simulation, that's kind of where we are now, where we're starting to, explore, early stage of the role of quantum. And this could be in sort of a weather and climate context, maybe something like atmospheric chemistry. So this is, the next stage for this community. They'll start to look at quantum simulation on its own. And then finally, you'll sort of, embed this into something that we'll call complex quantum sensing for now. And as you see, even touching on the previous slide around sort of integration and heterogeneity, we really believe that quantum will take a very similar trajectory in a number of use cases, obviously not just in weather and climate, but it's a good illustrative example. And so you really, when you look at industries today that do benefit from high performance computing, certainly things in automotive, doing things like computer aided engineering, airflow over the vehicle, for example, or aviation, where again you're looking at similar types of applications, all the way through finance and healthcare and life sciences, and pretty much any major vertical industry. They really today benefit from high performance computing, and we really see all of these industries being able to benefit in the future from a heterogeneous approach where quantum is a tightly integrated accelerator, and you'll see a similar trajectory as I just described in each of these. And at the end of the day, this is what we as an industry really owe all of these industries, our solutions, so that they can solve those most challenging problems. So when you look from a technology perspective, really what's going to happen, and it's already started, but it'll sort of grow over time, is, today we're very much, mostly focused on, what's labeled there as the quantum technology stack. And this is really mostly from the control technologies down to the QPUs. If you look at the technologies that you have in a current full stack quantum computer, this is essentially the parts that it covers. But really what we need to do over time to get towards that practical quantum computing and that heterogeneous computing that you need is we need to start to look more and more at the general computing stack and really ultimately how you tightly couple the two. And so what's interesting here is that this tight coupling between quantum and the higher level infrastructure will really occur at that quantum control layer, as it is that first layer where you encounter the quantum world. But in order to do so, is really, really important that you efficiently expose the unique requirements of quantum computing to the higher levels of the stack. And there are absolutely unique things to quantum, such as calibration, which is something that's really not comprehended today within a classical computing stack, but will be very important as you start to look at quantum technologies as accelerators. So a little bit about quantum machines. So really our focus is bringing out the best of any QPU. And this is something that we feel is really, really important, as ultimately architectures will embed multiple types of QPU architectures or modalities. It is unlikely that any single technology will win out. So when we talk about what a heterogeneous architecture will look like, it's likely to be composed of multiple types of QPU architectures. So that's really one that we bring out, is really focus on leveraging the performance of any QPU. The second one is very much around achieving the fastest time to results. And this today is very much around developer cycles, for example. As we talked about earlier on, there is still a lot of research that's being done into quantum algorithms, even down to the basic technologies of the QPU. And so really the ability to have very fast development cycles, to be able to perform the most complex operations and algorithms as fast as possible, is a very essential characteristics of the technology in order to move the industry forward as quickly as possible. So when you look at the quantum control, the quantum technology stack in a little bit more detail, this is really where quantum machines is focused. And this is everything from the higher level software layers with OpenQASM-3, for example, support for OpenQASM-3, down into the QUA pulse level programming language that is quantum machines developed, through to our very unique QM pulse processor technology, and then all the way out into the individual front-end technologies to support the different types of QPUs. So the quantum orchestration platform is the quantum machines approach to really building that foundation for practical quantum computing. So there's a number of aspects here that are really important, not only for today, but especially as the industry starts to scale up in terms of QPU counts and complexity, and touches on all those things that I mentioned earlier on around commercial grade, production grade, moving from the lab into this again commercial environment, and also being able to integrate into other types of infrastructure. So just to highlight a few things, it's designed for scale. That's everything from the performance of very complex quantum algorithms to supporting the growing QPU counts. It has the real-time capabilities, which is something that is very unique to the quantum orchestration platform. And this is critical for things like the advancement of quantum error correction. It also intuitively exposes the lowest levels of the stack and of the QPUs, so that we can really again expose and extract the best performance from any QPU. Designed for quantum classical algorithms. This was one of the core architectural design criteria right from the very start, when the company first developed the platform. And then finally about, it supports multiple quantum architectures, as we'll show in a second. So one of the very interesting things about the quantum orchestration platform is that it supports multiple gate-based architectures. In fact, all the major ones, and we sort of highlight a few of them here. Superconducting qubits, cold atoms, trapped ions, quantum dots, NV centers. It also supports photonics as well. And this is really one of the very interesting things about the platform, is that it is QPU agnostic. A little bit about the company. We were founded in 2018. We are the industry's largest, focused quantum control company. We have over 110 what we call quantum passionate experts. We're very proud of our team members. We have a number of them that are quantum physics PhDs, engineers, the entire spectrum that's necessary in order to build a technology stack and to support our customers as well. We have over 200 customers around the world, in 23 countries. And as I mentioned before, we're really, our heart and soul is really around being pioneers in real-time control, hybrid quantum classical capabilities, and multi-QPU support. These are just some examples of leading organizations that have selected quantum machines. This is across enterprise, startups, national labs, academic institutions. What you see here are government, academic. The enterprise ones are ones that we can't speak about publicly, but as an example, we are an OEM to a number of full stack quantum computer vendors. And we're really, really excited to announce our strategic partnership in Japan with Toyota Tsusho. I think the announcement went out last week, and this is something, again, we're just very proud of, very excited about. Toyota Tsusho is obviously a world-leading organization with world-leading customers as well. And really what this partnership is all about is joining forces between the two companies and their respective deep expertise and technology in quantum, and offering that opportunity to Toyota Tsusho's customers to really start to explore quantum computing and to accelerate those development cycles. And at the end of the day, really about being able to accelerate, towards the use of practical quantum computing. So again, we're very, very excited about this partnership, and hopefully you can learn more about it from Toyota Tsusho as well at the show. So just a few takeaways. Number one, the quantum computing market is at an inflection point. I think this is really, really exciting that where the industry has gone and is going to. And there's a number of things that are happening now that are really going to take it into that era of practical quantum computing. There are necessary factors or characteristics in order to reach that practical quantum computing, things like effective control, very tight integration, hybrid classical quantum computing. The third one, which again touches on this aspect of integration, is really around that, the investment into integrated high performance computing and quantum is on the rise. And we really see this as the first landing spot for a number of these quantum systems. And then lastly, quantum machines, we deliver the foundational infrastructure for practical quantum computing. We've been pioneers in this space for a number of years. And we look forward to being, contributing to the industry over a number of years to come as well. So with that, I thank you very much for your time and look forward to having a good show. Thank you.